Thanks for joining us on another video. This is kind of the third video on fluid dynamics. Today we're going to take a look at Blaise Pascal and his contribution to how do fluids move. Hopefully if you're watching this video, you've watched the other two videos on fluid transmission. And as a quick review, our first video we talked about fluids want to move from an area of higher pressure to an area of lower pressure. Perfect example, if I had a soccer ball, right, it's pressurized on the inside. If I poke a hole into the soccer ball, that air is going to rush out from high to low. The next video we talked about Bernoulli's principle. And what's great about that is it gives us a lot of the understanding behind why do planes lift off the ground, or why do frisbees or ultimate discs stay in the air. And again, it has to do with the idea that the faster a fluid is moving, it's going to create an area of lower pressure. So if I was in the lazy river, and if you get to that narrow section, if you watch it, tubers tend to go quicker. And why? Because there's an area of low pressure. They get kind of sucked or dragged into that area, and then get spit out pretty quick because it's lower pressure. So that brings us up to today with Pascal's law. Now, Pascal's law comes back from Blaise Pascal, who was a French mathematician and scientist. In mathematics, you might learn about the Pascal's triangle. I'm not going to delve into it today, but you can look at that. You'll probably learn that before you head up to high school. Now, Pascal's law in science has to do with fluid dynamics again. So we've talked about fluids, but what does this exactly mean for fluid dynamics? So for beginners, Pascal's law has a couple different names. It's also known as the principle of Pascal, and it's also known as the principle of transmission of fluid pressure. Okay, you see why I'm going to go with Pascal's law here. Okay, it's the idea, and most of the time we're talking about a confined area. So if I was talking about the fluid pressure in a soccer ball, it's confined into that soccer ball. If I'm talking about in a syringe or needle, it's confined to that needle. So there's a limited area where the fluid can escape, and we can kind of control that on a contained area. So keep that in mind. So now, what does it kind of state? It states that pressure exerted anywhere in a confined area is distributed equally in all directions. Okay, so let's explain this. All right, so the biggest example Pascal uses is this idea of a wooden barrel. So picture a wooden barrel, a really large one, so maybe it stored grains or maybe pickles, and it was simply filled with water. Now, if I were to press down on the very top lid on this pickle barrel, what's going to happen? Hopefully you get the idea that pressure is going to build. Now, what if we were to add holes on the sides all the way around it? Would the water come out equally? And the answer is yes. This is all Pascal's law. It's this idea too, if I had a soda can or if I had a water bottle and I were to press on the sides, okay, by just simply pressing or squeezing, what's happening is it's creating equal amount of pressure on the top, on the bottom. It's equal, and hopefully you're getting the understanding of that. If not, hey, I brought this lovely caulking gun here, okay? The whole understanding is this. Okay, I'll pull this out for you. Some of you guys are like, I don't know what that is. So this might be used around tiles. Maybe there's a crack in a window kind of around the outside and it seals it. This is a tube. It's a contained area. It's filled with a fluid. Okay, in this case, it's filled with premium elastomeric, okay, interior sealant. Okay, so basically it's a fluid. It flows out of the tip here once I open it. Now, kind of like that pickle barrel, if I apply pressure on one side, okay, if I kind of make this little clicking noise and I kind of press this little handle, it's going to increase the pressure inside, and if there is an opening, it's going to make that sealant come out. Okay, if I had a hole right here and I were to squeeze, it's going to come out this side and this side with equal pressure. Okay, now let's get down to the scientific examples that'll probably better help you understand this. And the first one has to do with shocks. Now, if you've ridden a bicycle recently, most bicycles now are coming out with shocks in the very front. Okay, if not, like my illustration, I made the shock part kind of red, and I made it this gray color. I kind of also made my little makeshift one right here. Now, the kind of the two part or the red part, okay, is acting as our shock. So if I were to hit a bump on those shocks, okay, the whole idea is that the tire moves up, it moves the shock, and quickly, right, that shock is going to press back down. It's not going to make my hands go wobbling up, right, when I hit a stump, when I hit a stick, when I hit some uneven bricks. Now think about it. Inside that red part, or in this case, my first bottom roll, okay, it's fluid filled. And we usually fill it with what's called hydraulic fluid, right? If you're sick, if you want to think of water, that's great. Water tends to leak, so we don't want to use water too often. So again, say you hit a bump, right? So here's the wheel, right? We hit a bump. It's going to press up on the shock, and what happens is this top acts as a piston. If you guys remember that syringe or that needle, it's basically sealed, right? And it's pressing down on the inside fluid. Now quickly, as it presses up, that fluid is going to try to compress. Now liquids such as water, hydraulic fluid are not great at being compressed. It's possible, but it takes a lot of extreme pressure. In this case, okay, what's going to happen is instead of it kind of really compressing, what it does is it presses back. So if I hit a bump, the shock goes up, the piston kind of stays where it is, it just applies pressure to the fluid and that makes it come back down. So bump, it presses back, right? It's kind of like hitting the spring on your mechanical pencil or pen where it just kind of bounces back after you hit it. Kind of the same idea, a little bit more complex. Now you see the shock example used not only in bicycles, but in cars and trucks and other vehicles. So I put a little diagram there just showing you that on a car, you might have 4 different shocks for each tire, right? So maybe only one tire hits a bump, right? One individual shock will go up and then press back down. If you were to have, you know, something where all 4 tires at the same time, all 4 tires are going to kind of affect that shock. Now think about it, this has a lot to do with not only having a fluid in there, but also making sure everything's sealed. So if the seal between the blue and the kind of like this cardboard color, if that seal's broken, fluid's going to come out. Or say for example that you apply too much pressure, right? This is a true story. So instead of my bicycle, I was driving my car, okay, and one thing led to another. My car ended up going off a cliff. Okay, it's about a 15-foot cliff. I had like 5 or 6 people in my car. Okay, it was like a little SUV. And what happened was I ended up hitting not just a bump, right? I went off a cliff. So when I hit the ground, my shocks went really high up there and the force was enough to break that seal. So it was no longer a sealed contained area. So what happens? It explodes and a fluid basically went out everywhere and my shocks were basically obsolete. They did not work anymore. Okay, so if you ever wonder like what happens if there's too much force for the container to hold, it might explode, it might break, fluid might leak. Okay, and again, it's not typically air, it's typically hydraulic fluid or something a little bit thicker than water. Okay, so let's get to a couple of different examples. We can use that pressure inside not only just to kind of like pump back, we can actually use it to accomplish things. And the next example I have for you is a backhoe or maybe some heavy machinery that maybe you might see at a construction site, right? So here I have a nice little kind of backhoe, okay, that's what I want to call it. And it has a couple different things. It has a couple different parts to the arm, to the bucket, and if you look, it has a part very similar to a shock. There's kind of like that piston, that rod, and there's kind of that container a little bit wider, and it's going to be fluid filled, okay? And there's different little hoses that run to make sure the fluids move. Now, if I have a way to control the fluid on the inside, okay, I can use it to move different parts, right? Mechanisms. And this is basically the understanding behind hydraulics. So take for example that shock, all right? We understand, okay, if I move a lever and I can make the piston go down, okay, I can make the shock go down, right? So if I move this, right, it's going to make the fluid inside squeeze and it's going to press down. Okay, I understand that. If I'm in a construction vehicle and I press down on a lever and it makes the piston go down and I leave an area where on this side I have another seal and it almost looks like a different piston, I can, when I press down on the lever, I can make this part go down. So instead of that fluid building up pressure, it actually causes something else to move. And if you look carefully at each different part of that arm of that backhoe, right, if I move a lever on the inside, okay, it sends fluid down a hose, okay? That hose is going to make, rather than just build up pressure and nothing happens and releases it back, right? When I push the lever doesn't come snapping back. It makes a different part move. So that might, I press the lever and that might make the backhoe arm move, or it might make the bucket go forward or backwards. We can kind of control the hydraulics. Okay, our last example here is something you're going to use on a daily basis, and it has to do with driving a car. So one day you're going to get your license, you're going to be driving down the road, and say for example something jumps out on the road, a deer. And what do? Your immediate reaction is you slam on the brakes. What happens next? What's happening in the mechanics of your car? And you don't need to be an auto body person, mechanic to understand this. This has to do with Pascal's law. So we press on that brake pedal. Okay, that little rectangle, what's going on? I'm gonna bring this back, sorry. But when you press the brake pedal, it's attached to a piston. Okay, and that piston is going to move forward, and we have that area of a contained fluid, brake fluid. So I press on the brake pad, it moves the cylinder, and inside that fluid, rather than just build pressure, it causes another piston to move out. So as that brake pedal presses in, right, it's going to cause another part to move out. And what does that do? That might cause a different hose to fill up the fluid, and that gets sent down to our brake pads. So basically that fluid moves down and it fills up and presses on two pieces of ceramic or different kind of composite material, and it slows down the tire. So from brake pad, right, to a piston, which builds that fluid pressure, and then it sends another little piston which causes that fluid to kind of squeeze on that tire. Now, again, look at that diagram. It's really complicated as far as breaking down all the individual parts, but the idea is the same every single time. As we cause one area of a contained area, so whether that's a cylinder, okay, whether that's a box, whether that's a ball, if I apply a pressure to it, okay, I'm doing that by using a piston in those last couple examples, okay, it's going to want to react. And it's going to react with an equal force. So it's either going to force this piston come back, or it's going to cause another piston to move and cause some other basically mechanical action. Whether that's the backhoe arm moving, whether it's the brake pad squeezing against the tire. This is all going back to Pascal's law. Now there's a bunch of different uses for Pascal's law and hydraulics, okay? You can make your whole career out of just fixing these, right? It has to do with basically being contained, whether it's in hoses, whether it's in these cylinders. There is some sort of fluid, and rather than the pressure building, okay, it's causing some mechanical action. Okay, it's the same idea behind most car jacks, which are made for commercials. Maybe the lifts that are in car shops that actually lift the vehicles off the ground. They're all using hydraulics, and they all have to come down to Pascal's law. Again, if the pressure builds too much and the fluid can't hold it, or that container can't hold it, that's where we get leaks, that's where we get explosions, that's where we get hoses popping off, and we got hydraulic fluid, brake fluid spraying everywhere. Really, really messy, okay? If you ask anybody who's a mechanic or anybody that works on these machines, I may have broken a few of these parts in my days of working other places. It does get messy, but it comes down to how do I fix it? How do I contain that pressure, that fluid? Pascal's law. So hopefully you enjoyed today's video. Hopefully you enjoyed the examples. I just want you to have a basic understanding of how do fluids move, how are they contained, how are they used to make other actions. So make sure you subscribe, watch our next videos as we jump into different units, different parts of science. Thanks for watching.